Alright, this video is going to cover Chapter 13 on planning and conducting experiments. Alright, I know that you guys said you didn't really want to necessarily do PowerPoints, but I know that my handwriting gets kind of bad, and I want you to be able to take nice notes to follow in your note sheets, so I typed kind of a lot of this stuff out. There is a PowerPoint available through my website, like I showed you guys, that follows most of these notes and goes over experiments, stuff like that. So if you're interested in using those PowerPoints for added help or added notes, please feel free to take a look at that. All right, so planning and conducting studies. We're going to use this example here to kind of help us get a grips on it. So I'm going to refer to this example often as I go throughout this notes. Researchers are interested in whether or not a new calcium pill can help improve bone density and relieve arthritis. So the idea is to create an experiment that will do that. First off, an experiment versus an observational study. In an experiment, we impose some change or treatment and measure result or response. So in an experiment, we force something upon people, or we make them take something to see if that is going to cause a change, or to see if we can measure a change, or measure some type of response from that treatment we put on people. So that's an experiment. In an observational study, like we said before, we just simply observe. So the biggest difference is that in an experiment, we can suggest a cause and effect relationship. Right? We call that a causal relationship, a cause and effect relationship. So that's the main difference between an experiment and an observational study, is that we can actually say in an experiment X causes Y. There are four main principles, and we're going to talk about these principles real briefly here. I want you to write them down, but as we move throughout the lesson, we will learn more and more about each one of them. The first main principle, I know there's three here, I'm going to list the fourth at the bottom. The first main principle is in any experiment is we have to have control. Now I wrote possible confounding variables must be controlled for, so we'll talk about what we mean by confounding variables. But the idea is in an experiment, you want to have a lot of control. You, as the researcher, control everything that's occurring. Randomization needs to take place as well. That's the second main one. This should be used in assigning which subjects should be placed into which groups for treatment. So you want to randomly determine what subjects get each treatment, or maybe you're in the control group that get no treatment, but you have to allow randomization to figure that out. We oftentimes do have to use volunteers in an experiment because we are forcing something upon people, so we kind of do have to have volunteers. That doesn't make it a poor example. Like we talked about in the past, volunteers is bad for sample surveys, but in an experiment you kind of need them. But the randomization comes into who gets what. We'll talk a little bit more about randomization later. Also, natural variation in outcomes, that should be in outcomes, can be lessened by using more subjects. We call this replication. Okay, and that is actually the official name of this third principle, is replication, meaning that if you only have one subject using the calcium pill and one subject not using the calcium pill, I mean, what are you going to learn from that? Oh my goodness, the guy taking the calcium pills, bone density was so much better. Well, you know what? There's a bunch of other factors that could have contributed to that guy having better bone density and lessening his arthritis besides that calcium, because it's just one person. But if you witness a group of 50 people have a significant change over a group of 50 that don't take it, then all of a sudden it's meaningful. Or heck, 1,000 people you notice a change for everybody as a group versus 1,000 people that don't take the pill. That is more important, obviously more meaningful, and that's replication, just using more subjects. The fourth principle is kind of like a fourth one with an asterisk. It's not necessarily, it doesn't have to be included, but it's called blocking, and it's the principle of blocking. And blocking is a way of assigning groups in a little bit of a different way. It's a lot like stratifying. But we will talk more about this later. The reason why I put it with an asterisk is it doesn't have to be in every experiment, where the first three actually do have to be in every experiment. All right, the variables involved. There are two important variables involved. The explanatory variable, that's the X, we talked about that before, explanatory, and the response variable, that's the Y. The explanatory variable is the actual variable that we control or change. So in my problem, it would be the actual calcium pill. We call it a factor, okay? The calcium pill is a factor, and that factor could come in different treatment levels. What I mean by that is maybe we have three groups, okay? And one group gets 100 milligrams of the calcium, another group gets 50 milligrams of the calcium, and the third group gets no calcium pill. Okay, they'd be like our control group. So I still have one variable, the calcium pill. It's just coming in three different treatment levels, 100, 50, and none. So I have one factor, calcium pill. Does calcium affect arthritis? Does calcium affect bone density? So, but I'm going to look at it in three different treatment levels. So if you understand the difference between the treatments there. The response variables, what are you going to measure at the end? What are you looking to see? I'm looking to see, did the bone density get stronger? Did the arthritis pain go down? So that's the kind of stuff I'm measuring at the end. Okay? The two variables that I don't necessarily want are confounding variables is one of them. A confounding variable is another variable that occurs and you're like, crap, was it that variable or is it the calcium? And a good example here that I want to mention is, for example, if all of my patients lift weights, then all of a sudden lifting weights could become a confounding variable. Meaning at the end, if I said, wow, all of my patients lifted weights and took the calcium pill, oh boy, was it the lifting weights that caused the bone density to increase, or was it the calcium pill? I don't know. See, I didn't control for lifting weights. I didn't really think about lifting weights, but I found out at the end that they all lifted weights. So which one did the causing? Was it the lifting weights that caused the bone density to go up, or was it the calcium? Oh boy, I don't know. That would be a confounding variable. We obviously want to try to get rid of confounding variables so I don't have any confusion there. Another type of variable we don't want is what we call a lurking variable, and the other name for a lurking variable is an extraneous variable. This is, again, it's another variable that actually drives all the variables. Okay, so this is another variable. An example that I want to talk about here in my example could be milk, for example. If everybody was taking milk, boy, milk causes more calcium, and milk can cause bone density to increase. So is it the milk that's doing it, or is it the calcium? So it's kind of that same idea of a confounding variable. And I know you might be like, extraneous variable, confounding variable, what's the difference? There's not really a big difference. Oftentimes we just say a lurking variable is something that we see at the very end and we're like, crap, we didn't even think about that. We totally forgot about milk. Oh my gosh, everybody was drinking different levels of milk. Maybe it was the milk that was causing their arthritis to go away, not the calcium pill. So again, these lurking variables, confounding variables, are just other variables that can do the causing, and we don't want them to. So we have to control for them. Who are the people that are involved in these research experiments? The three people involved is the researcher themselves. That is the head person. The researcher's the know-all. You know, he's the Wizard of Oz. He's the guy behind the door that's controlling everything. He knows who's getting what. He knows who's taking the placebo, who's in the control group, who's taking the 100 milligrams, who's taking the 50 milligrams. He knows all that. We also have the subjects. Now, subjects are officially called experimental units. That's kind of like the official term. Now, subjects could be people, animals, plants, objects. Subjects can really be anything. So we, oftentimes subjects are referred to as people, but if they're like plants, for example, we want to see if a new fertilizer can cause plants to grow better or something, then we would call them experimental units. But subjects, experimental units are the same things. Those are the people that are taking part in the experiment. And we also have the evaluators. These are the people that are going to measure the response variable at the end. These are the people, these might be doctors that are going to actually measure the bone density, because I don't know how to do that, and the doctor would know how. Or again, these could be the doctors that are going to talk to the patients and determine if their arthritis really has gone down. So these are the people that are going to measure the response variable at the end for me. So I'm the researcher, got subjects, got the evaluators. One of the biggest things in an experiment is the idea of control. I mean, this is extremely, extremely important. Why do we need control in an experiment? Because control allows us to get rid of confounding or lurking variables. We always must worry about being sure that our factors, calcium pill, is actually causing the effect and not something else. So we need to establish strict control to make sure no other variable is doing the causing under our nose. Okay, there are many issues to watch out for, plan for, and control for so they don't happen. So I like to refer to this as leveling the playing field. Level the playing field. And that means that I want all of my subjects to be as similar as possible except for the calcium pill. That's what I'm controlling. So I don't want half my subjects drinking milk and the other half not drinking milk, because then maybe it's the milk that helps them. I don't want half my subjects lifting weights and the other half not. So again, I want to level the playing field. I want to make everybody the same except for the calcium. So I could establish strict control by telling people nobody drink any milk while you're involved in this experiment, or everybody drink a glass of milk a day. At least it would be kept the same for everybody. Or nobody lift any kind of weights, nobody do any exercise, or everybody do some exercise. That way I'm leveling the playing field. I'm making sure that everybody is the same except for those that have the calcium pill, those that don't. So that's how I want to make sure I establish strict control. You may say you can't make everybody drink milk or not drink milk, or everybody lift weights, not lift weights, and we'll talk later about how that can be controlled for by actually using randomization. Also, control groups. I really hope that everybody understands a control group. Control group is a group that actually does not receive the treatment. This group gives us a group to compare the results to. So the reason why we have control groups is that we use them as a comparison group. I mean, if all I look and say, oh wow, these 50 people bone density got better. Well, better than what? How much better? I don't know. Maybe they just naturally went up or something. I need something to compare them to. That's the control group. You do not have to have a control group. Maybe you just want to see if this calcium pill is better than another calcium pill, or if a new calcium pill is better than some old calcium pill. So you're just comparing old versus new. Then you wouldn't necessarily need a control group, but they are oftentimes used. A placebo is something that you use in a control group, okay? And a placebo is a pill, or it's a treatment that is fake, okay? It's not real. And here's the idea of why we need a placebo. We need a placebo to get rid of what we call the placebo effect. See, the basic idea is that when you're involved in an experiment and you know, all right, I volunteered to be a part of this experiment, you're going to think that something is going to happen to you. Oh, I'm going to take this new pill. Wow, I'm going to get better. I'm going to have better bone density. My arthritis is going to go away. I just know it. So sometimes a lot of people experience the placebo effect. The placebo effect is simply you think because you're getting something, it's going to do something for you. So if I have a group of people that know they're taking a pill because they're taking a pill every day. They know they're taking a pill. And I got another group of people that are just my control group that I say, no, you guys are just doing nothing. Don't change anything. Then all of a sudden that group of people says, oh, I'm not getting anything? No wonder my arthritis is getting worse. No wonder my bones are feeling more frail, because I'm not getting anything. This isn't fun. What the heck? What's the fun of being an experiment if I'm not getting anything? So we want to level that playing field. We want everybody to think they're getting something. So we actually use a placebo so that everybody thinks they're getting something. Everybody thinks something is going into their body. Whether it's fake or real, everybody at least thinks they're getting something. So the placebo effect refers to changes in the subject caused by the attention of the experiment itself. Again, sometimes just being in an experiment makes people think that they're going to get better or get worse. So we want everybody to experience this. So to control for the placebo effect, we use a placebo. So using a placebo it helps us to get rid of the placebo effect. So using a placebo makes everyone think they are getting something to get rid of the placebo effect. And usually, like I said, in an example where it's pills, it's just a sugar pill. Now, if you're using dogs don't know any better. They don't have brains like humans do. So you might not necessarily have to have a placebo when you're working with animals or plants. If you're going to use a new fertilizer versus not using a fertilizer, you don't have to make the plants feel like they're getting a fertilizer. They don't know any difference. They're plants. So usually placebos are used with human subjects. We also have blinding and double blinding. Again, I hope a lot of people know what this is. Single blind experiment is where the subjects do not know what they're getting. So obviously a placebo helps with this. There are situations where you can't blind, but it is best to have the subjects not know what they're getting. Now, you might be doing an experiment where 100 people are going to use a new exercise program that involves a lot of stretching, and other people are going to use another exercise program that doesn't involve stretching. Now, obviously, those people know what they're doing. You can't blind them to what they're doing in these exercise groups. But if you can blind, it is a great idea. And blinding is that way people do not know what treatment they're getting. Double blinding refers to when the subjects don't know and the evaluators don't know. Why would we not want the evaluators to not know what they're getting? Well, if I'm a doctor and I know that somebody got this placebo or this calcium pill, I might be like, oh wow, your bones do feel stronger. Oh wow, your arthritis is going away. Oh wow, that pill is really working. And I mean, most doctors wouldn't do that. You would hope, but again, you never know. And you, as a researcher, need to establish control. So you want those evaluators to treat everybody the same, whether they took something or they didn't, or they took a pill or they took a placebo pill. You want the evaluators to treat everybody the same, and the only way to guarantee that is to blind them so they don't know what people are taking. Do we need blinding and placebos in experiments? It's not always feasible. So not every experiment has these. You can still have experiments without them. They're not musts, okay? Just so everybody knows that. Randomization. I really want to emphasize what randomization is and why it's important. This must be performed to determine who gets into the treatment groups and the control groups. So who gets what needs to be the randomization. Sometimes you have to use volunteers, and that just, you've got to do it. But randomization actually helps to minimize the effects of lurking variables and confounding variables. What I mean is this. Let's say that we think milk can have an important impact on bone density, and so does exercise. But we cannot make people drink milk or not drink milk. We cannot make people exercise or not exercise. So we just allow randomization to hope that the control group that gets the placebo and the other group that gets the calcium pill, we just hope randomization will put different people in both groups, meaning that some people in the placebo group drink milk, some don't, some exercise, some don't. In the actual treatment group that gets the calcium, some drink milk, some don't, some lift weights, some don't. The idea is that we hope randomization mixes the groups up enough so that lurking variables and confounding variables kind of go away. They kind of get minimized. If I don't use randomization, I could have everybody in my placebo group drink milk. That would be a bad thing. So hopefully randomization mixes up those that drink milk between the two groups. Or if I don't use randomization, everybody that lifts weights could be in the calcium pill group. And then that's why they got better joints and bones, because of that, not because of lifting weights, not because of the calcium. So again, hopefully randomization will evenly disperse those people between the two groups. It does seem reasonable, for example, to hand sort subjects so all groups have the same number of women, same number of Catholics, same number of Hispanics, same number of short people, and so on and so on. But it's not good. Okay, the best method is to be randomly placed. Okay, and you're like, what are you talking about, Catholics and women? I'm just saying, like, you want your groups to be mixed. And some people say, well, if I pick them by hand, I can guarantee they're mixed. You don't ever want to pick by hand. You need randomization to mix those subjects up. If you have enough people, they will get mixed up through randomization. Special note, in the experiment, the randomization does not refer to how the subjects are selected from the population, but how they're selected into the treatment groups. Remember, you need volunteers in experiments. You can't just grab 20 random people off the street and say, you have to be part of my experiment. No, you kind of need them. So remember, we need those volunteers. The randomization is who gets what treatment group. Randomization balances unknown sources of variability. So again, the unknown of milk being a factor, randomization should balance milk drinking people into both groups so it doesn't become an issue. Okay? So hopefully a lot of this makes sense, okay, in terms of these main things here. We're going to do plenty of examples in class that it makes a lot of sense, but hopefully it makes sense. The last thing I want to talk about are the three types of experimental designs, okay? Any good design produces causation, maintains control, and reduces variability within treatment groups to make it easier to detect differences amongst groups. Let me make sure that makes sense. First off, a good experiment can show that X causes Y. A good experiment, you have control. You level the playing field as much as you can. And a good experiment makes in each treatment group, for all the people getting the actual calcium pill, we want those people to be we want to reduce the variability within that group as much as possible, which meaning we want those people to be a nice mix. We want them to have a lot of things in common. We want them to be similar, but we want to make sure it's the calcium that's doing the causing, not something else. Okay, so the three different types are completely randomized design, a randomized block design, that's that fourth principle blocking we'll talk about here in a second, and a matched pairs design. We're going to go through these a lot in class, but I want to briefly go through them right now for you. A completely randomized design means subjects are randomly split into the treatment groups. Each subject has a complete equal chance of being placed into any of the groups, relies solely on randomization to control for extraneous variables. So again, the idea is very simple. If I had 100 volunteers, I'm going to give everybody a number 00 through 99. I'm going to use a computer or a random number table. The first 50 numbers chosen, ignoring repeats, will go into the placebo group. The other 50 will go into the treatment group getting the calcium pill. Completely randomized design. If you say, well, what about people drinking milk? Randomization will split those people up evenly, hopefully. You just have to count on it. What about people that exercise a lot? Randomization will split those people up between. What about women versus men? Because men have better joints anyway. Well, okay, randomization will evenly split men and women up between the groups as best as it can. That's completely randomized design. A randomized block design is if there is one variable, maybe there's one variable that we have to control for. We absolutely cannot let randomness control for it. We have to control for it. So this helps for lurking extraneous variables by bringing them right into the picture. So if you are absolutely convinced that exercise will have the biggest impact on joint health and you don't want randomization to just evenly split up people that exercise, then what we do is we split them up. We block. Okay, block is a lot like stratifying. So we have a block here, and this block is people that exercise. We know these people exercise. This other block right here, this is for people that are non-exercisers, okay, if that's even a word. So this isn't random. This is, hey, we know these people don't exercise. We know these people do. From these people that exercise, we randomly put half of them into the placebo group and half of them into the treatment group. I know you can't read that too well, sorry. And again, this would be done randomly. Once we have those people that exercise separate, we say, okay, half of you randomly get placed into the placebo group, half of you randomly get placed in the treatment group getting the calcium. Of those that don't exercise, once again, half get into the placebo group, half get into the treatment group. That would be done randomly. This way, we can really take our results. We can compare within those that exercise. We can compare within those that don't exercise, and then we can compare all of the people together as well. So it's almost, think of blocking as running a separate experiment on each block. So we're going to separate those that exercise, run a separate experiment, and then on those that don't exercise. So this is for, you can only block at one variable at a time. You cannot block on two variables, one at a time. You have to pick what you think is the most important. Matched pair design is actually very interesting. Here, subjects are purposely, not randomly, purposely paired together because they have something in common. One of whom receives the treatment while the other receives the second treatment. So, I'm going to take two people. Why would I pair two people together? I would pair them because they're both men. They're both in their 30s. Okay? They both have similar health. They both exercise the same amount. They both drink milk. Their two men are about as similar as possible. Then, randomly, one gets the placebo, one gets the calcium pill. Now think about that. Those two men are as similar as possible. Now I could really tell, does my calcium pill do the causing? Yes or no? Now I want to have obviously many of these pairs. I don't want just one pair, so I'm going to have another pair, maybe two women that are in their 40s. Pair them up. One gets the placebo, one gets the calcium, chosen randomly. Maybe I want to pair up two people that are in their 20s, two males, both about the same height, both about the same age, both have the same exercise habits, they both drink the same milk, they both have the same diets. Pair people together that are extremely, extremely similar. Then you could give one the pill, one the placebo, and really determine, did that pill help that person? You can't tell me, oh, it was because he exercises, that's why he got better. No, it wasn't. They both exercised. Well, it was because he drank milk. No, it wasn't. They both drank milk. So matched pair designs are really good as well, but sometimes they don't work. But for the most part, they are pretty good designs. All right, so the last main principle I want to talk about one more time is just replication. Replication is just making sure that you have enough people in both groups, okay? We'll talk about measuring results. I don't want to spend a ton of time here, but the idea is that when you're all done, you have the placebo group versus the actual calcium pill group. You want to determine, is the difference between those two groups statistically significant? So that's a big word that we're going to talk a lot about. Is the difference statistically significant? Did the difference we saw occur because of the calcium, or was it just due to natural variation? Hey, any two groups of people are going to vary. I mean, it's the truth. Any two groups are going to vary. But did we see a difference because of the calcium pill, or because of just, hey, everything varies? That's the decision you have to make. We'll talk a lot more about that as well. Here's a couple summary points. I'm just going to leave them up here. You can write them down if you want to. They're just kind of some important things to mention. So if you want to write them down, obviously pause the video, write them down. Here's a couple more. Again, pause the video, write them down. These are a couple more important summary points. And here's a couple more. Again, pause the video, write them down if you need to, and so you can understand these main points. And here's one last slide here. Again, write it down if you need to. Pause, write it down. We'll talk a lot about all these things in class. All right, guys, thanks for paying attention. Hope you have a great weekend or a good week or whatever. And take these notes. We'll check them in class.